Well, we have seen for the example of a polytrope of index n equal 4 that for very high frequencies we can actually follow the procedure by filling in nodes for P standing P mode, or for very low frequency we can fill in our oscillatory region for the G mode range. We can fill in the nodes to construct a standing G modes, but in between we have a domain where we can have both a G mode propagating or a G mode oscillatory region and a G mode oscillatory region at the same time for a mode. So if we consider this as a standing wave, we cannot distinguish whether it's a G mode standing wave or a P mode standing wave. The character of this mode is not determined. It has a mixed character. It's neither a G mode, neither a pure G mode, nor a pure P mode. But this can be understood, of course, by the remark that a strict Sturm-Liouville problem is only found for radial adiabatic modes. It is no longer a Sturm-Liouville problem, and therefore also no natural classification scheme for the modes does exist, where we can associate with a number of nodes in the eigenfunction, where we can associate the order of a mode. So there is in a strict mathematical sense, there is no ordering scheme, and the ordering schemes adopted by several authors, well, these ordering schemes are adopted for convention. If we are mathematically strict, then we would say this ordering scheme or the classification is rather deliberate. It has no strict mathematical justification. So keep this in mind. Strict mathematical ordering scheme is only available for the radial adiabatic modes. Well, another point might be mentioned, the G plus modes. Well, you can discuss, of course, with the dispersion relation of G modes, you can discuss both signs of n squared. N squared positive means we have a convectively stable region, and n squared negative, it means we have a convectively unstable region. And you can now discuss the sign of k squared depending on the sign of n squared and on the sign of omega squared. In the convective region, we have the omega minus modes, which are the unstable modes representing the convective instability. And in the once n squared is positive, we have positive omega squared. These are the G plus modes, and we can discuss now the propagation properties of omega of the G plus and G minus modes in the various domains where we have either convective stability or convective instability. That means where we have negative and positive signs of the Brand-Weseley frequency. And if we do this, you can discuss the sign of k squared depending on sign of n squared and omega squared, and you will find the following properties of the G plus and the G minus modes. The G plus modes oscillate in the convective. The G plus modes, these are the stable, neutrally stable modes, oscillate now with respect to the radial dependence. Do not confuse time and spatial oscillatory behavior. So they oscillate with respect to the radial dependence in the convectively stable, in the radiative region, whereas the G minus modes oscillate with respect to radius in the convective region, and they are evanescent in the other region. So the G plus modes are evanescent in the convectively unstable region, and the G minus modes, they are evanescent in the convectively stable regions. This is just a matter of discussion of the the sine of k squared, depending on the sines of n squared and omega squared. Okay, well, the last remark here is the propagation diagrams have so far been discussed and developed for adiabatic pulsations, and they are strictly useful or maybe used in a strict sense only if we consider adiabatic pulsations. The question is whether they are also applicable in non-adiabatic environments. The answer is largely yes. You can apply also this discussion with respect to oscillation, propagation, evanescence, exponential decay, also for non-adiabatic environments. But of course, it is not derived. It is not derived for these environments. So you have to be careful once you interpret the behavior of a certain mode with respect to propagation, and you have a highly non-adiabatic environment. So actually it's found to be applicable, but you should be aware that it's not derived for this case, and you in certain cases may lead, in certain cases you may get misinterpretations, so be careful. But in many cases, it's also applicable for non-adiabatic environments. Okay, now let's go again to our models. Well, we have discussed the propagation diagram for the polytrope of n equals 4. This is given here. And, well, we have here the run of the frequencies of the radial frequencies as a function of time for some stellar model. So these are the frequencies. Here, for instance, the mode G1, G2, F, P1, P2 as a function for the stellar model, initiating at some time t. This is the model which now starts to evolve through the HR diagram. And what we see here is, well, the G modes here in the initial model, the P modes and the G modes are well separated. This might be a case where these two oscillatory or oscillation domains do not overlap, and this may change now during evolution, so that the G mode propagation region overlaps with the P mode propagation region, and this means that the G modes increase in frequency, whereas the P modes almost stay at a constant frequency. And then these strange modal diagrams are found where the G mode, once it meets the so-called F mode, it seems to avoid this crossing. Here it seems to avoid the crossing with the P mode and so on. And this gives a rather complex and bewildering picture of the frequencies once the star evolves and the propagation region within the star simply shift or extend, or in some sense they overlap with the G mode. The G mode propagation region overlaps with the P mode propagation region. So this change of the propagation region is seen here in the run of the frequencies as a function of evolutionary stage or as a function of time. Okay, well, here we have described again the propagation properties of G plus and G minus modes. Here we have a convective region, A is bigger than 0, and here we have a radiative region, a convectively stable region. So we have a propagating region for the G plus modes and an evanescent region here for the G plus modes in the case of convective instability, and the opposite is true for the G minus modes. The G minus modes propagate in the convectively unstable regimes, and they have evanescent behavior in the convectively stable regimes, determined by A smaller or bigger than 0. Yes? Pardon? No, this is just a schematic picture how the propagation properties of the G plus and G minus modes appear. This is without any reference to any stellar model. It's just assuming that these hedged regions are convectively unstable and the unhedged region is convectively stable. And then we will find this propagation behavior that the G plus modes propagate in the stable region, the G minus modes are evanescent there, and the opposite is true for the convectively unstable regions. Then the G plus modes have evanescent behavior and the G minus modes propagate there. Okay? No reference to any stellar model here. Okay, well, with respect to the question whether these propagation discussions, evanescence discussions are also applicable to a non-adiabatic problem, well, I have to present to you some accident, the results of some accident which happened to me some time ago. Well, I calculated the non-adiabatic frequencies and the eigenfunctions of an extreme hydrogen deficient carbon star, of an extreme helium star. And what I ended up with, well, I used the Riccati method, which we have discussed as a method to calculate or to efficiently and accurately calculate the eigenfrequencies. And what happened, one of these modes took more than half an hour to integrate or to determine the eigenfrequencies. And I was a bit puzzled and thought, what might be the origin of this long computing time? And I went to see the eigenfunction, and maybe I get some information through the eigenfunction what happened to that mode. So plotted here are two components of the eigenfunction. So the eigenfunction consists of 8 components. We have 4 temperature, pressure, luminosity, and the Lagrangian displacement times 2, because these are complex quantities. So as an example, we have 2 components of the eigenfunction here, given as a function of the logarithm of the pressure of the hydrostatic background model. So here logarithm is small, so here we have our photosphere, and down there is the center of the star. So it doesn't look very surprising. We have the maximum amplitudes at the outer boundary, close to the outer boundary of the star, and the amplitudes of the eigenfunction decrease more or less exponentially towards the center of the star. So nothing really happens here, and it was not clear why this takes so much computing time. So then I went and expanded the scale of this eigenfunction. Well, the eigenfunction is normalized to unity. The eigenfunctions are always determined only up to a complex constant. Why? Solutions of the perturbation problem, which are the eigenfunctions, are determined only up to a complex constant. So we can always multiply the eigenfunction with a complex constant, and we can get again an eigenfunction. So why is that? The reason, we have a linear system. So the system, the perturbation equations is a linear equation, and the solutions are determined only up to a complex constant. So this is normalized to unity. This is the maximum amplitude which appears here. So what's going on here? Now let's expand simply the scale here, going from -1 to +1, and let's expand it a little bit. What happens? Well, first of all, we see some more oscillations on the outer edge of our model. Well, this is also expected, because this is a typical P mode decays exponentially, and there are some additional modes here, additional nodes here. But once you go here, it starts suddenly oscillating again, and it starts rapidly oscillating once we go to higher values of log p or further inside the star. So this occurs to oscillate around log p around 40, and if we expand this scale even more, then we end up with a rapidly oscillating part of this eigenfunction with low amplitude, with amplitude 10 to minus 4, but rapidly oscillating. And here we have an oscillating part, whereas this seems to be some barrier for the mode which shields or screens the oscillating regions in the center of the star. Well, how could we interpret this? Well, we resort to the propagation diagram or the propagation properties of a wave of this kind. Well, so what we do then is we consider the propagation diagram for this mode. The horizontal line is the frequency of the mode we have determined, and the lamp frequency is the dotted line here, whereas the Brand-Wasserli frequency is this line denoted by stars given here. So, according to our understanding, where are the propagation regions? The mode will propagate once the frequency is bigger than both the Brand-Wasserli and the lamp frequency, and the mode will propagate once the frequency is below both Brand-Wasserli and lamp frequency. This is obviously true here in this region. Sorry, it's now the opposite. It's now left and right hand side are exchanged. The boundary of the star is here, log p equal 10, and the center of the star is on the right hand side. So at the outer boundary we have a propagating region here in this domain. The frequency is bigger than both Brand-Wasserli and lamp frequencies, so it will propagate there as a p mode. Then we have a small evanescent region, and then the frequency at the same time is then smaller than both Brand-Wasserli and lamp frequency. It's much smaller. That means it corresponds to a high order G mode there. So it's much smaller than these two frequencies, and it enters a propagation region which extends essentially down to the very center. So what we expect is propagation out here as a P mode, propagation down there as a G mode, and a evanescent region around log P around 25. Okay, what do we see in our eigenfunction? Well, around log P 25, there seems to be the oscillations seem to go away. So we have this is, so to say, an indication for the evanescent zone, and we have P mode propagation out here and G mode with high order of modes. That means with many nodes in the center of the star. Well, you see, afterward, even if we haven't thought before calculating this mode, a posteriori we can interpret the behavior of the mode using these propagation diagrams. At the same time, I apologize for the advertisement. This is done by the Riccati method, and you see the how powerful this method is, even without knowing the run of the eigenfunction and the run of the equations or the run of the variables which we need to integrate. It reliably calculates both also the domain where we have very high very strong oscillations with very short wavelength and highly a strongly oscillating function, which for resolution will need lots of points, which is not accessible through matrix methods, because in order to resolve such a fast oscillating function, you need so many points that your matrices will become ill-conditioned, and you cannot really calculate the resulting linear problem. This is not a problem for the Riccati method, being a shooting method where you can just follow all these oscillations. It just needs a little bit of time, and that's what I saw. It took quite a lot of time, half an hour computing time, to get through all these nodes and calculating all these high frequency, highly frequent behavior of the eigenfunction. So that's an example, first of all, how the propagation diagrams may be used to explain the run of the eigenfunction, and also a demonstration of the capability of the Riccati method. Okay, so let me just give you a small illustration of what we found so far. Well, in a schematic way, the modes which we found so far may now be described as the G plus and G minus modes, if we have convectively stable or convectively unstable domains. So we have either G plus or G minus mode. They have a maximum frequency, which is the Brand-Weiseley frequency, and with increasing order, they approach zero frequency. Here the frequency is given as a function of the harmonic degree L. Then we have the P modes, whose frequencies have a minimum frequency and whose frequencies increase with the radial order of the mode, and which have accumulation point infinity. Let's come to the F mode later. And the non-radial modes have a limit for L equals 0 for the radial mode. Once you consider the P modes have a finite limit also for L equals 0. These are the modes which we have considered in the previous lecture. Okay, so what we are left with now is, now we can go and calculate the spectrum of non-radial adiabatic modes for a given stellar model. Well, many stars are sufficiently well described by adiabatic approximation, and for these stars, which include our Sun, we can determine the adiabatic spectrum, or in other words, the spectrum of non-radial adiabatic modes. We can compare the spectrum, the calculated spectrum for the respective stellar model, compare it to the observed values, and then we may use the discrepancies either to improve the pulsation code or the pulsational description, or we could also use it to constrain the stellar parameters or constrain the stellar models, which provide an agreement of the spectrum of the calculated spectrum of the modes and the observations. So we use the discrepancy to constrain the stellar parameters. We look for those stellar models which fit, for which the theoretical results fit best to the observed values. So, for instance, for the Sun, for which adiabatic approximation is not bad, we have the following theoretical result. Well, we have again here the frequency is given as a function of the harmonic degree L. We have the spectrum of P modes. Well, again, the classification in terms of P1, P2, and so on is not unambiguous. but people nevertheless do it. These modes are called the P1, P2, and so on. This is for a stellar model. These are the results for a stellar model. Then we have the so-called F mode, and then we have the spectrum of G mode, with the highest frequency being the Brand-Wasserli frequency, and with increasing radial order, the frequency decreases, and finally the limit of the G modes is zero frequency. This is for high degrees of the high harmonic degrees, this diagram, so it looks nice and fine. But if you go to lower degrees, even for the stellar model, then you will find that if you enlarge this part here, so from 0 to, you enlarge the part from harmonic degree 0 to 25, what you see, well, the P modes seem to enter the G mode regime, and also this F mode seems to cross first the G1 mode, or the mode which is called G1 here, then it crosses the G2, G3, and so on. And this crossing of modes led the author to identify the F mode, what he says is the F mode here, this mode with F here, but this mode with F here. And accordingly, this is no longer G1, but this is called the second one is now called G1. I would not agree with this classification, and I will tell you later on, and you will see later on, why I would not agree with this classification, and why this mode is the F mode still at this position, and down there. And the G1 mode is still the mode on the right-hand side of the crossing and on the left-hand side. And this one remains the G2 mode from here to here, even if it is crossed by the F mode. Where does this come from? Where does this crossing come from? It's due to the fact that for the high high order G and P modes simply are well within the propagation region for P modes, and well within the propagation region of G modes. Whereas if you go to lower order modes and low degree, then you will end up with a propagation diagram where you have for a certain given frequency, where you have both a propagation region for G modes and P modes for the same modes. And this is reflected in the modal diagram, where you find then crossings between the different set of modes. You see here that G1 mode enters or seems to cross the P1 mode here. It's actually not very nicely resolved. But these crossings and overlapping of the modes is associated with the modes having a mixed character, where the same mode has two propagation regions, one as a G mode and one of a P mode. This as a result of the determination of the spectrum for a solar model. Okay, we can describe it in terms of the propagation diagram. So this is a propagation diagram for the sun and the modes shown above. Once you have very high order P modes, it's fine. You can associate only the propagation domain for P modes for the high order modes. The same is true also for the high order G modes. This is, for instance, given by this horizontal line. The P mode is given by this horizontal line. We have only one propagation region, which is definitely a P mode propagation region here, and which is definitely a G mode propagation region here. In the intermediate range, once we take a mode with frequency in the intermediate range, then we have a propagation domain for this mode, both in the G mode regime and in the P mode regime. So this mode has a mixed character, and this is associated then also with the mode crossings between P and G modes, so they can no longer uniquely or unambiguously be defined as P and G modes. Okay, this is as an example, and we are now almost at our have arrived at our aim. We are now in the position, for at least for those stars for which the adiabatic approximation is reasonable, and these are very many stars, including our Sun, to compare the result of the theoretical calculation with the observation, and thus to determine those stellar or solar models which fit those solar models which provide theoretical frequencies which are close to the observation, and thus constrain stellar parameters and stellar or solar models which are thought to be the realistic or those which are close to the reality. Okay. Well, we have seen several times this strange. It's not a strange mode, but it's seems to be a strange mode in between the G modes, which we understand, and the P modes. There seems to be another mode which is labeled with F, and to see or to understand where this mode comes from, I would like to go to some other problem, or to a problem which explicitly allows for a representation of this kind of F modes. Well, finally, to close with this chapter, we consider the non-radial adiabatic pulsations of a very, very simple model, namely of the polytrope of n equal to 0. Why do we do that? It's not because this is a very realistic model. It's by no means realistic, but this problem can be solved analytically, and we can follow each mode or the properties and the frequencies of each mode analytically, so we can see what actually happens. Okay, to remind you, n equals 0 polytrope is a star for which the density is assumed to be constant, and we have explicitly calculated the pressure stratification in that star. The pressure is given by central pressure times a parabolic profile, so this goes with 1 minus radius over the 1 minus radial coordinate divided by the total radius of the star squared. We also saw that for this object, or for this configuration, the Brand-Weserly frequency is negative, so we have convectively unstable configuration, and we expect only G minus modes. Okay, I don't want to take you through the entire mathematics, because that's rather complicated. This is rather time-consuming, and it's rather technical. So I don't want to take you through all the analysis. Well, just a few things which I want to say. It's in this case the potential. The Poisson's equation decouples from the rest, and due to this decoupling, the perturbation equations, reduce to second-order problem, which then can be solved analytically in terms of hypergeometric functions. You probably will not be familiar with hypergeometric or confluent hypergeometric functions. Well, these are functions which have been studied in detail in the last, or in the 19th century. So we know a lot about the properties of these hypergeometric functions. So the solution can be given in terms of hypergeometric functions. And finally, if we go through all the analysis and adopt the normalization that now sigma squared is the dimensionless frequency, it's a little bit, the normalization is a little bit different from that which we have used so far. It differs by a factor of order unity. Adopting this normalization, then we end up with the following formula, analytical formula for the eigenvalues. n now does not denote the polytropic index, but it counts the radial order of our modes. So we have an index counting the nodes, the radial nodes of our eigenfunctions, and this number counting the order of our nodes is, of course, a parameter of the eigenfrequency. So what we end up with is that sigma with index n and l, the eigenfrequency depends on the azimuthal wave number or on the harmonic degree L, and on the radial order of the mode. And this is given then by dn plus minus, so it's a solution of a quadratic equation, dn plus minus dn squared plus L times L plus 1 to the power 1/2, where the upper sign, the plus sign, denotes the p modes and the minus sign denotes the g minus modes. We do only have g minus modes. Well, with dn being explicitly given by the adiabatic index, of course we expect the adiabatic index to occur there because it's a parameter of our equations, so it appears also in the solution for the eigenfrequencies, and it depends on the radial order n and the azimuthal degree L. Well, that's even too complicated for us, so we consider the limit of radial order going to infinity, but this is a closed analytical form for the eigenfrequencies of this homogeneous n equal 0 polytrope. And so we obtain for the p modes, we obtain as an approximation for n going to infinity that sigma n L squared is given by n squared times the adiabatic index plus L times L plus 1 over gamma adiabatic n squared. So this is the spectrum, resembles the spectrum of p modes for this polytrope, for this for this homogeneous model. And the g minus modes, they go with L times L plus 1 over n squared. Of course, these are g minus modes, so this is negative here. So they go with the ratio of the azimuthal order divided by the radial order. Well, so we have the spectrum of p and g minus mode for this configuration, and well, these solutions also allow for a singular solution of these equations, which is called the F mode or the Kelvin mode. This mode, there's only a single mode left apart from the G minus modes and the P modes, which is given by, or which is determined by the harmonic degree L only. Of course, there is no index n left because this is not a sequence of modes. This is just one mode, which depends on the harmonic degree and which does not depend on the adiabatic index. So the adiabatic index, gamma adiabatic, does not appear in this mode. So it's independent of gamma adiabatic. Well, for L equals 0, sigma f is 0. It does not exist for spherically symmetric perturbations. Well, it does. It's also 0 for L equals 1. So it's 0 for L equals 1. So for L equals 0 and L equals 1, this F mode does not exist. It's only present for L bigger or equal than 0. Well, the independence of the adiabatic index means that this mode will also be present once we have no compressibility. So even in the incompressible environment, this mode will still exist because the lack of the appearance of gamma adiabatic means that compressibility does not play a role. Okay, so well, actually, if you look for the eigenfunction or for the behavior of the eigenfunction of this mode, it consists of a deformation of the surface which is achieved without compression. consider a homogeneous constant density configuration, which you do not compress, but you deform the surface of this configuration. Well, then you get this mode. This means this mode represents a surface wave on top of your configuration. No compression is involved. It's a surface wave. Okay. Well, a surface wave in spherical geometry. Well, you cannot have a surface wave in spherical geometry keeping the volume of your star fixed, because if you want to change the volume of your star, then compressibility will enter. Compressibility will be important. So this means surface wave with spherical geometry is not possible. You have to deform your surface wave. That means spherical symmetry is not possible. That means this mode vanishes for L equals 1. Why does it vanish for L equals 0? It's not present. But why does it not appear for L equals 1? Once this is a surface wave traveling on the surface of our star. Why is L equals 1 not possible? L equals 0, okay, we need to distort the surface in order to have a surface wave. With spherical geometry, it's not possible. But why is the L equals 1 F mode excluded? A surface wave with the geometry of L equals 1. Well, how does it look like? So let us write down how it looks. Let's take our original homogeneous star, constant density. This is our original star, and let us deform this star with an L equals 1 perturbation. Then this is the center of our star. Well, L equals 1 would look like this. This would be an L equals 1 perturbation. So why is such a surface deformation? Well, of course, the volume is kept constant here, no problem. Actually, this configuration should have the same volume. It's my drawing which is misleading here. So the volume stays constant, but it's the deformation of the surface into one direction. Now that seems to be excluded. Why? Think in terms of the conservation laws we have to satisfy always. Which conservation law is contradicted if we have such a perturbation? Well, it's the conservation of momentum, or the conservation of the point of center of mass. Center of mass needs to be conserved, so the position of the center of mass needs to be conserved. If we keep the volume constant and have an L equals 1 perturbation, we would have to shift the center of mass. And in the case where it's not possible, and this is true here, this means such a perturbation is not possible, and therefore L equals 1 is excluded, and the lowest harmonic degree for which the F mode can appear is the perturbation for L equals 2. Okay? Center of mass or momentum is not conserved for L equals to 1, and so this mode is not present for L equals 1, and this explains the dependence of sigma F squared in terms of L times L minus 1 here. This describes the F mode, and that's essentially the physics of the F mode. It is a surface wave traveling on the surface without needing any compression, and this can only be done for L bigger or equal to 0. Well, despite the fact that the classification in terms of G minus, P modes, G plus modes, and F modes has been done on the basis of very simplified and idealized models, this classification is also adopted for more sophisticated models just to get a classification. But one should keep in mind this classification is coming from very idealized, simplified models, and it's not clear and it's by no means justified in a strict mathematical sense to adopt this classification for more sophisticated stellar model. Okay, the rest I've already commented on. Well, we are now in the situation to compare calculated frequencies with measured frequencies, and thus we are able to identify suitable solar or stellar models. Well, in general, modes have mixed character. We have already comment on that, and modes are not well ordered, and we have indications that modes cross each other during the evolution or as the function of the harmonic degree. So keep this in mind. We will come to these mode crossings and what happens at a mode crossing later on. Okay, so we have now finished with the adiabatic stuff, and we go on. The natural next chapter then would be dealing with linear non-adiabatic treatment of stellar perturbations. Okay, so I would need then the next file, non-adiabatic analysis. Now, in this case, we do not have many analytical tools to describe or to interpret the results. We have to perform numerical solutions of the linear non-adiabatic equations, which means we are dealing both with the mechanical and the thermal structure. We are now taking into account not only the mechanical part. The adiabatic approximation largely takes into account the mechanical part and reduces the thermal influence only to a relation between pressure and temperature or pressure and density, whereas we're now going and considering in detail the thermal equations, and we solve them using, for instance, the Riccati method for radial and or non-radial perturbations for a given stellar model. The result of this analysis is the spectrum of eigenfrequencies. Now the eigenfrequencies do not only have a real part, and instability is no longer achieved with negative values, through negative values of the eigenfrequency, sigma squared being negative, but we have real and imaginary parts independent of each other, and we determine the real and imaginary parts independently for the full set of equations, and of course we can also calculate the associated eigenfunctions. Once we have done that for a particular stellar model, then again we can, at this stage of the analysis, we can now go to observations, or the opposite way, we select an observed model, and it's an observed pulsating star. We construct a model for this star, and we perform the linear non-adiabatic radial and or non-radial analysis. We end up with periods here. We end up with damping and growth rates. And once we find an unstable mode, meaning that the sigma I is negative, then we might think that this mode should be observable or might be realized in the observed stars, and we could then try to compare the associated frequency and compare it to the observed period. So this is done also here in this institute, has been done several times. This is the approach which is at the end of this analysis. We can directly compare periods with observed periods with theoretically calculated periods, and we can determine which modes which modes should be seen because they are excited, because sigma I is negative, and therefore this mode should grow and might show up in the observed periods. Okay, so this is the practical purpose, or this is the way which we have in principle originally aiming at. We are doing some theory and compare the theory to observations. Now we are at the stage where we can do it. Observe pulsating stars, make a model for the star, perform the stability analysis, obtain unstable modes, and obtain their periods, and compare now the periods with the observations. And well, if there is a parameter which is not known, for instance, the mass is always a parameter which is badly known from observations. So we can perform this analysis for different stellar mass, for different models which are different in mass, and we may then select this model or the mass of may then take the model with that mass which provides periods which are closest to the observation, and we may thus determine the mass of our object. So the observation of periods may lead in comparison with the results of the linear stability analysis and a comparison with observed periods to a determination of the mass of the object which provides the pulsations. So in that case, it might lead or might provide a tool to determine or to restrict stellar parameters, and to restrict or to identify those stellar models which for the observed objects are have the highest likelihood to be the correct or to be appropriate models. Okay, well, another point, once we have an instability, of course, would be, well, we would like to understand this instability once we found in a bit more intuitive way, or in other words, we would like to identify the mechanism which provides the instability which we found numerically in the numerical analysis of, or the numerical consideration of the pulsation equations. Okay, so another aim, and we'll follow this line now in the following, we would like to see what is the instability mechanism behind a negative value of sigma I found in the computations. A particularly useful tool, once we have the computation, to identify which might be the underlying instability mechanism for a negative value of the imaginary part of the eigenfrequency is the so-called work integral. This work integral is developed on the basis or on the hypothesis that an instability, that our stars are big heat engines, and during pulsations they transform or transfer heat energy into mechanical energy. Well, once a star pulsates, we have a kinetic energy. This kinetic energy must come from somewhere, and the hypothesis is or consists of saying, well, this mechanical energy, the kinetic mechanical energy, is ultimately generated from or taken from the heat content of our star. There is no other energy source from which the kinetic energy could come from, rather than gravitational or equivalently the thermal heat content of our star. So the star must, if this hypothesis is right, the star must act as a huge Carnot-type heat engine which transforms heat energy into mechanical energy. Okay? So it's a big diesel engine operating in the universe. Okay, so let's consider, once we're talking about transfer of heat energy into mechanical energy, we have to go back to thermodynamics, and we consider the changes of state of a mass element in a pressure volume diagram. Okay, so take a mass element within our star. The mass element, it has a certain pressure and a certain volume, and during a pulsation, during a cycle of a pulsation, we consider the path of this mass element in a pressure volume diagram. So if the motion, or if the pulsation is perfectly cyclic, a perfect circular or perfectly periodic motion, then this will be a closed loop in the pressure volume diagram. If it's perfectly periodic, then we'll start somewhere here, pressure becomes smaller and it increases here again, comes back to the same position. So in general, this path of a mass element within the pressure volume diagram is enclosing a certain area in the pressure volume diagram. What does this area in the pressure volume diagram mean, or how could we interpret this? Well, PDV is the work done by the mechanical work done by the mass element, or it is the work which is the mechanical energy which is dissipated by our mass element. PDV is the thermodynamic work either done by the mass element or consumed by the mass element. In this case, well, at this branch, if the pressure is falling and the volume is increased, what is the work done? Is it done by the element, or is consumed by the element? There is work done by the element, which is just the integral below this branch. If we go back in the opposite direction, then it's the work which is consumed by the element. So this has to be subtracted from the work done by the element. So the area within this loop corresponds to the work either done by the element or consumed by the element, depending on whether we go in clockwise or anti-clockwise. If we go clockwise, then it's the work consumed, and in the other direction, it's the work dissipated by or consumed by the mass element. So the work done or consumed by the element can be positive or negative, depending on which direction we go. The work done by the element, which is called W dash, or the differential work integral, is the integral over PDV around one circle of the pulsation. So we need for this representation, we need actually a periodic process. This cannot be defined without a periodic process, as any heat engine needs a periodic process. Otherwise, you cannot run the heat engine. Okay, so it's classical thermodynamics of heat engines, which we are doing here. And it's a closed loop for periodic pulsation. Area within the loop is the mechanical work provided or dissipated during a pulsational cycle. The sign depends on whether we go clockwise or anti-clockwise. Okay, well, now the hypothesis is that our pulsation works like a Carnot-type process, like a heat engine, converting the thermal energy into mechanical energy and vice versa. And the mechanical energy which is produced, we have considered and denoted as the differential work integral. So we would like to know how big is this for a given mass element at a certain position within the star. How big is this differential work integral? How big is this energy which is taken from the heat energy and put into mechanical energy, and thus put into kinetic energy of the pulsation? Okay, So during pulsation of its kinetic energy or is increased or dissipated by per mass at a rate, the change of the mechanical energy per time is given simply by the pressure perturbation and the change with time of the density perturbation. This is simply PdV or delta P times delta V, because delta rho is 1 over the volume. So this corresponds to the rate at which the energy is mechanical energy is generated or dissipated, and we would like to know for the mass element how big this really is. In fact, if we go through the analysis, then we can actually calculate this from the eigenfunctions of our perturbation problem. This W dash defined before can be obtained by taking the imaginary part of the pressure perturbation times the complex conjugate of the temperature perturbation. So what would that be in the adiabatic case? Pressure times temperature. Well, this refers to the eigenfunction of our perturbation problems in terms of the pressure perturbation. So this is the pressure perturbation part of the eigenfunction, and this is the temperature part of the eigenfunction. What would happen if the changes of state would be adiabatic? Adiabatic means T is nabla adiabatic times P. What would happen? So as a result of evaluating this quantity here, I have stated, or I claimed that within a suitable average, for instance, over one time cycle, over one period of pulsation, or if we take a suitable ensemble average, then we end up with the formula that the differential work integral, the work per unit cycle or per time transferred from the heat to mechanical energy, is given by the imaginary part of the quantity pressure times the complex conjugate of the temperature perturbation. What would happen if this would be an adiabatic pulsation? Adiabatic means T is nabla adiabatic P. Then we would have P times T star would be P times nabla adiabatic is real P star. So P times P star is real, and the imaginary part is 0. Okay, that's consistent with our approach, because if it's an adiabatic pulsation, then we cannot transfer. Adiabatic means there is no heat transfer between the element and its surroundings. So this means we need non-adiabatic changes of state to get a heat transfer from the internal heat of the star to mechanical energy. Consistent with that, this quantity vanishes once we have a adiabatic changes of state. And this you also see here in the case of adiabaticity, temperature and pressure are in phase, are proportional to each other, and this proportionality, or the phase difference between pressure and temperature perturbation, leads to a transfer of heat from the heat content of the star to the kinetic energy. Do we need to stop here? Okay, it's a good point to stop here, and I will finish. I will finish then with this part tomorrow, and we'll discuss it a little bit, and then we're going to more exciting, or even more exciting than processes working on this basis, more exciting processes for stellar pulsations. Thanks.